and start the screen sharing, unlike what I did last week. Okay. Would someone just give a little shout out to tell me that you can see the screen okay, everyone?
Yes.
Yes, we can.
Okay, great. So I think you'll
Yes.
recall that last week we finished with this diagram, which showed the directions of all the lines for all the different modes of decay. And the last question I asked you was, of course, this, what mode of decay was associated with each of the different lines. And that was the last slide of modes of decay. And now we're going to start on interactions of ionizing radiation with matter. The key word there, by the way, is ionizing. There are lots of kinds of radiations that travel at the speed of light. They're electromagnetic, but they're not ionizing. For example, visible light, ultraviolet light, infrared light. Those are not ionizing radiations, and most of what we're going to talk about will not be applicable to those kinds of radiations. We're going to be specifically talking about alpha, beta, plus, beta minus. Those are the particles. And then X-rays and gamma rays, those of course are the photons. And the first of these interactions that I would like to discuss with you is what is called Bremsstrahlung production. Brems, B-R-E-M-S, is a German word for deceleration or slowing down or braking, like when you brake your car. And Strahlung is the German word for ray or radiation. So since some German physicists first came up with this concept, the term is referred to as braking radiation. Here's what's involved. We have a fast moving, and here's the key word, a charged particle. We're not talking about a neutron, but a fast moving charged particle, like a beta minus particle or a beta plus particle. And when it comes near a nucleus, there is either an attractive or a repulsive force that will change the direction of the path of that particle and slow it down. And anytime anything slows down, whether it's a photon, a beta particle, or your car, anytime anything slows down, energy is given off. In the case of your car, when you hit the brakes, your brake parts get very hot. The heat is a form of energy, but that's not the case at all when we have a beta particle plus or minus. So let's take a look at a diagram. This is similar to diagrams in every physics book on the planet, basically. And here's what we have. Let's first look at beta minus. Here's a beta minus particle cruising along. It's probably traveling at 1/3 to 1/2 of the speed of light. So it is going extremely fast. Now, that beta particle doesn't hit this nucleus. It just comes close to it. And what kind of force do we have? We have an attractive force because we have an electropositive nucleus, an electronegative beta particle. Now, if you'll carefully follow the pointer, that nucleus is trying to do the following. It's trying to take this beta particle and pull it in and capture it. And it could do it except for one thing. It's going so fast that it cannot capture it. It's like shooting a steel bullet past a magnet and having that magnet capture the steel bullet. Not possible. It's going too fast. But what does happen is that the beta particle slows down, it changes path a little bit, curves down in this direction, sort of in the direction of the nucleus, and X-rays are given off. Now, these are not characteristic X-rays. They do not have a finite number associated with them. And instead, it's simply a spectrum of X-rays. That's all that it is. The Bremsstrahlung production associated with a beta plus particle is almost exactly the same conceptually, except that instead of an attractive force, we have a repulsive force. So as you can imagine, beta particle, this beta plus particle comes zinging along here. This electropositive force from the nucleus is going to repel the electropositive force here. It's going to push that beta particle away from the nucleus. It's going to slow it down. And again, we will get these non-characteristic X-rays. So it doesn't matter whether it's a plus or a minus here. The only difference is that one's an attractive force, one's a repulsive. Otherwise, the diagrams should be identical. And keep in mind, those X-rays are not characteristic. Now, everything that I've said just now is pretty much documented in the next two slides. So I'm going to fly right through them. Beta minus particle, there's an attractive force. Its path is changed a little bit toward the nucleus. And with the electropositive positron, there's a repulsive force pushed away from the nucleus. But in both cases, there is a loss of energy in the form of X-rays. Okay. Now, that has more to do with X-ray rather than nuclear medicine, except that sometimes, for example, in the case of a microsphere study with yttrium-90, yttrium-90 will emit characteristic X-rays and characteristic and possibly non-characteristic X-rays. We might do a Bremse-Strahlung scan, not for quality, but just to make sure that we have placed the drug in the right place and that it didn't drift off somewhere else. So we can image those X-rays, but not with very high quality. What is the most important effect of all, and the most desirable, is of course photoelectric effect. And here's what's happening. We have a low energy gamma, typically. Low energy means like technetium energy, I-123, relatively low energy. And this gamma ray will collide with an electron. It transfers all of its energy, every bit of it, and the photon is gone. And all of the energy of the photon was transferred over to the electron. We call that an inelastic collision because the photon didn't hit that electron and bounce off. It transferred 100% of its energy. And so the photon is completely gone. That is a totally inelastic collision. If it transferred only part of it, like in the Compton effect, then we would say that that is a partially elastic collision. And in the rare case where a photon hits something, bounces off, and loses no energy at all, that would be a totally elastic collision. One example of an inelastic collision might be the following. If you take a mud pie and drop it on the table, it's not going to bounce back because it gave up all of its energy when it hit the table. On the other hand, if you have one of those little balls that were called super balls, maybe as a kid you remember playing with them, if you dropped a super ball, it would hit and bounce back perhaps 80% of the way. The next bounce would be 80% of the first 80%, and so on. That would be a bunch of partially elastic collisions like we're going to see in the Compton effect. But the one we desire is photoelectric because there are no secondary gammas that could interact in the crystal in the wrong location. So here's what we have. A photon hits an electron. That electron is ejected from whatever orbital it might be in. And we will say that the kinetic energy of the electron equals the energy of the gamma ray that struck it, minus, we have to overcome the binding energy holding that electron in its orbital. You know that electrons are in orbitals around a nucleus, and everything is very stable because the forces for that electron leaving and for that electron staying are equal. The force, by the way, of removing an electron from an orbital, to give you some insight into the size of the force, is that it's measured in electron volts. Electron volts are very tiny compared to keV, kiloelectron volts. So here's your equation. I'll show you. Let me go to your equation first. This says that the energy of the photoelectron equals the energy of the gamma ray that struck it minus the binding energy of the electron in that orbital. But this is a very small number, and It's not exactly true that the energy of the gamma ray and the energy of the photoelectron are exactly equal, but it's pretty close. So if you see this equation, someone asks you, I'm going to ask you on one of the practice exams, which effect is this associated with? The energy of the electron equals the energy of the gamma ray that struck it minus the binding energy. That is the photoelectric effect. And a more mathematical way to write the equation is the following. That is, the energy of any particle in motion is 1/2 mv squared. That's the mass and the velocity. This is the energy of any photon. It's h nu. H is Planck's constant, and nu is the frequency, and phi, the Greek letter phi, represents the binding energy. Now let's go back to the diagram. Here's what we're looking at. We have that incoming photon. It hits this electron right here, dead center. The photon is gone. It gave up 100% of its energy to this electron, totally inelastic collision, and the electron is ejected in this direction. And we call that a photoelectron because a photon knocked out the electron. And what happened? We left a vacancy right here. And what always happens when an electron is ejected from an orbital is that an electron from a higher up orbital drops down, fills the vacancy, and CXR, that's characteristic X-rays, are given off, and those characteristic X-rays could eject more electrons. Those are called Auger electrons, named after a French physicist, Monsieur Auger. And Auger electrons are really defined as electrons knocked out by the secondary process. The primary process here is that the incoming photon knocked out this electron. The secondary process is that these X-rays that were produced as a result of the primary process knocked out some more electrons, and those are Auger electrons. A good example might be, how penetrating are Auger electrons? Do they contribute much to internal radiation dose? The answer is yes, they do, because Auger electrons don't travel more than a few millimeters. What does that mean? They're depositing 100% of their energy in the patient's body. They can't escape. They wouldn't be imageable if they could escape, but they can't even escape. So we don't like Auger electrons because all they do is confer dose and they're not imageable. Let's take a very quick review. Incoming photon knocks out this electron. This electron drops down to fill the vacancy, characteristic X-rays, and Auger electrons. Now, I think you've all played pool once upon a time. Let's take a look at this example. The cue ball, if you're lucky, will hit this 8-ball dead center. The cue ball is going to stop right here. The 8-ball is going to roll into the corner pocket, and you win the game. What kind of collision is that? Elastic, inelastic, or partially elastic?
Inelastic.
Which one?
Is it inelastic?
Good, that's totally inelastic. What happened here? The cue ball transferred 100% of its energy to the 8-ball, and the cue ball just stopped dead right here. It's not moving anymore. That is a totally inelastic collision. And this is a mechanical example that is very analogous to our quantum mechanical example that we looked at in that diagram of the photoelectric effect. Now, I'm going to show you two questions. I have not taught you this yet, but you might have seen it somewhere along the line in a physics book, or perhaps your instructor taught it to you. But here are two questions right off of old exams. In which one of the following is photoelectric effect most likely? We have air, which is very low density, the patient, which is higher density, a sodium iodide crystal, which is higher than that, and the lead collimator, which is even more dense than any of those. Which one of those is most likely to cause a photoelectric effect to take place? Anyone? So the correct answer here is the lead collimator, and here is why. The photoelectric effect is most commonly observed when the Z number of the absorbing material, and that correlates very well to the density, is high. So the higher the Z number, the higher the likelihood of the probability of photoelectric effect. Now look what this is telling you. It doesn't say that the probability of photoelectric effect is proportional to Z. It's proportional to Z cubed. That means as Z goes up, the photoelectric effect probability goes up on a dramatic increase. It's a cube relationship. So if this is doubled, if we go Z to 2Z, this goes up by a factor of 8 because 2 cubed is 8. So it's almost a parabolic curve going up very rapidly. So that's the formula for the absorbing material. The probability is proportional to Z cubed. You could even think of it as density cubed, and you would still come up with the correct answer. So again, here were your choices. Let's look at the Z numbers. Air, nitrogen, and oxygen, number 7, number 8. We humans are made out of what? Carbon, hydrogen, oxygen, nitrogen, sodium. We are low Z material. The sodium iodide detector, sodium is number 11, but iodine is number 53, and lead is number 82. So that, of course, would be the big winner. Now, here's another related question. For which one of the following isotopes is photoelectric most likely to occur in a sodium iodide thallium crystal? Now, this is going to be based upon the energy of those photons. So first of all, let's see who can tell me what are the energies. I'll name one of these isotopes and maybe you could tell me what the energies are. How about thallium? Anyone?
70 and 167 keV.
Good. So thallium has about 70 or 71 keV. Those are the X-rays. And there's like, I think, a 135 and 167 keV gamma rays. So thallium is pretty low. Most of what we image is 71. Technetium?
140.
140. Indium-111 has 2 photons.
173.
Good. 173 and 247.
247, yeah.
Now, cobalt-57, we, as you know, don't image with that ever. We don't ever inject it, but that is one of the most important isotopes on that screen because what do we use it for? So we perform gamma camera quality control with cobalt-57. We have a flood source. And why do we choose that? Cobalt has an energy of 122. Technetium has an energy of 140. They are so close that it's a very valid assumption to say that if it works for cobalt, it's going to work for technetium and it's going to work for I-123. They're all, this is 122 and this 159. They're all pretty close to each other. And so I think that was probably all 3 of them. This one's 159. And so what's the dependent factor? The photoelectric effect is actually more likely to happen at low energy, and the Compton effect is more likely to happen at high energy. So we want to rank these in order of energy. We've really done that. Thallium is first, then cobalt, then technetium, then iodine, then indium. And so we're going to say that thallium is a big winner. And look again, we have a cube relationship. The probability of photoelectric effect is not proportional to energy, but e to the -3. That's the same as 1 over E cubed. That is, as the energy goes up, the probability of photoelectric effect goes down dramatically by a cube relationship. So the correct answer here is thallium, because this is the lowest energy that we have to deal with. Now, if we combine those two, this is probably the most important formula, and look what it says. Probability of photoelectric effect varies with Z cubed over E cubed. And that tells you everything you want to know about probability based on the Z number or density and the energy. So here are a couple of little problems that I've given you. And if you happen to have the lecture notes in front of you, I changed this question just yesterday and I added a couple more little options in here. But let's take a look. It's Z cubed over E cubed. Now, if we double Z and double E, what happens to the probability? Does it go up? Does it go down? Or is there no change?
Is it no change?
No change.
Excellent, right? This is going to be, if you double this number, that's going to be 2 cubed. This is going to be 2 cubed. They're going to cancel each other out. If you double both, no change. Let's go to the next one. What if you have Z and have E? Same thing, right? It's going to be 1/2 cubed over 1/2 cubed, and it's going to cancel out. So these two, numbers 1 and 2, will be no change. But let's look at the others. If you double Z and have E, then what's going to happen? Is it going to go up or down, and by what factor? So if you
It'll go
double Z,
up, for
that's going to be 2 cubed. If you have E, that's going to be 1/2 cubed. So you've got 8 divided by 1/8. That means it's going to go up by a factor of 64. And if you have Z and double E, then you're going to have 1/8 divided by 8. That's going to be 1/64. So here are your answers. In these first two, the probability is unchanged. In the third one, when you double Z and have E, it's going to go up by a factor of 64. And when you have Z and double E, it's going to go down by a factor of 64. Okay. Any questions about photoelectric effect before we move on to internal conversion? Anyone? Okay, good. Internal conversion is diagrammatically almost identical to photoelectric effect. There's only one line in that diagram that's different. Now, let me just take you back for a moment. Okay, here you'll see that the photon came in from somewhere else in the world, not from in this nucleus, but somewhere else. It interacted, knocked out this electron, and this whole scenario happens. Now let's go back to here. The only difference is the source of the electron. In internal conversion, the nucleus is highly energetic. The nucleus is able to transfer energy to an inner shell electron and knock it out. It is not doing that by emitting a photon. It's not real clear how that process happens, but energy transferred from the nucleus ejects an electron. That is going to be a totally inelastic collision. And here's your diagram. The only line that's different is this one right here. Remember that in photoelectric effect, a photon came from outside the nucleus, hit an electron, ejected it. Here, the energy leaves the nucleus, knocks out an inner shell electron. There it is. We call that an ICE. This process is called internal conversion because the excess nuclear energy is internally converted within one atom into the kinetic energy of this electron. And then we're going to have this electron, as before, drop down, fill the vacancy, characteristic X-rays, Auger electrons. Anytime any process knocks out an electron, we're going to get these X-rays, we're going to get Auger electrons, even if it's visible light or some other kind of electromagnetic radiation. Anything that ejects an electron will result in X-rays and Auger electrons. Now, I don't see why this would not be applicable, but I've never seen it in a physics book before. But it seems to me that we should be able to say that the energy of the ejected internal conversion electron equals the nuclear energy that ejected it minus the binding energy. Makes sense to me, but again, I've never seen it in the book. Okay, any questions about internal conversion? Please keep in mind that the diagrams for photoelectric and internal conversion only differ by that one factor. Where is the gamma coming from? Outside the nucleus or from the nucleus? Okay, next is the Compton effect. You all probably are very aware that the Compton effect is associated with the word scattering. It always will be because unlike photoelectric effect and Compton effect, you always get a gamma 2. We'll see in the diagram where that came from. And gamma 2 could interact in the crystal just like gamma 1 did, but in a totally different location. So that you have two different loci, two different places in the crystal, making the computer think that they came from two different places, but they didn't. One of them came in, interacted, moved laterally in the crystal for gamma 2 and interacted somewhere else. It doesn't happen a real high percentage of the time, but it's enough to impact the image quality and the resolution. So we're going to have what's called scattering, and the higher the energy, the more likely you are to get Compton. So if someone asks you, which is more likely to produce Compton effect, technetium or I-131? A very simple question. I-131 has a higher energy than technetium. It's 0.3644 of an MeV. It's going to be a lot worse for Compton than technetium will. Now, as you might imagine, that since a photon is coming in, knocking out an electron, and gamma 2 is bouncing off, this is going to be a partially elastic collision, and an electron will be ejected, and a higher up electron will drop down to fill the vacancy, and we will get characteristics and Auger electrons. Now, here's what's happening. This incoming photon, we'll call it gamma 1, hits this electron right here, knocks it out. There it is, Compton electron named after Mr. Compton, a physicist. And gamma 2 is deflected down opposite this one, not 180 degrees, probably never, but at some angle. It's an indeterminate angle. It could be anything. And that exiting gamma, we call gamma 2. It's not a new gamma. It's simply gamma 1 with the residual energy after the collision took place. You know it lost energy knocking out this electron. So the energy of gamma 2 will always be lower than gamma 1. But remember, this is not a new gamma. It's just the same gamma, but deflected at some angle from its original path. Now, what equation do we have before? It was easy. E electron equals E gamma minus binding energy. There's nothing simple about this equation, but let's make some sense out of it. The change in wavelength of gamma 1 and gamma 2, we can measure that actually, is equal to a bunch of constants. This is Planck's constant, mass of the electron, the speed of light, minus one minus cosine of angle phi. Now, angle phi, therefore, is the only variable in this whole equation. This is a constant. This is measurable. We don't know what angle phi is, but let's define angle phi. It is the angle between incidence and deflection, the line of incidence and deflection. And I'm going to ask you a question about that in just a minute or two. So here are the definitions of all these terms. Delta lambda, change in the wavelength. These are the three constants. And phi is the angle between incidence and deflection. This is a board question, a common board question. Where is angle phi? Is it angle ABD, ABC, CBD, or the very infamous none of the above? Where is angle phi? Anyone?
Would it be ABD?
ABD? Not a bad guess, but unfortunately not correct.
So ABC.
ABC? Not a bad guess, but unfortunately not correct. None of the above. That's the answer I like. Think about this. What was the line of incidence? This gamma was coming this way. If nothing got in its way, it would have gone straight, just like this. But it was deflected down from the line of incidence to the line of deflection. So angle phi is EBD, which of course in my initial question would have been none of the above. Angle phi is also 180 minus ABD. That would be this. So just keep in mind, it's the angle between incidence, the line of incidence, and deflection. And while this diagram kind of indicates that angle CBE and angle DBE are equal, you should not assume that at all. They not only don't have to be equal, they probably never are equal. I think I probably drew it without thinking about what happens to the angles. But just remember, the angle between incidence and deflection is gamma 2. Okay, now let's play pool one more time. Here we have another mechanical example that correlates to our quantum mechanical example. What kind of collision is this going to be? Just looking at it. Here's a cue ball. It's going to hit the 8 ball on the side. The 8 ball is going to roll into the corner pocket. The cue ball will go its merry way, different direction, lower energy, but the same cue ball. What kind of collision? Elastic, inelastic, partially elastic?
Elastic?
Not elastic. Did the cue ball give up all of its energy?
Partially elastic.
Yes, thank you. It gave up part of its energy, therefore it's going to be a partially elastic collision. If it gave up all of it, it would have been that pool table example we had 5 or 10 minutes ago, where the cue ball stopped dead right here, but it didn't. It was deflected down. So this is analogous to the Compton effect, just like we had the gamma that came in, knocked out the electron, and the gamma was deflected down, just like this pool table example. The very final interaction that I want to discuss is pair production. What I'm going to tell you about this, I don't mean this in a sacrilegic way, but only God knows why pair production exists. It was predicted before it was ever discovered by Albert Einstein. It has no utility whatsoever, nothing practical other than to give you one more thing to have to worry about for a board examination. But there are always pair production questions, so let's nail this down. It's not too hard. Anytime a gamma ray has an energy greater than or equal to 1.022, but almost always greater than, here's what can happen. It doesn't have to happen, but it can happen. And this is, I've bolded what's really important. It has to be in the presence of matter. The matter could be a solid, a liquid, or a gas, but it cannot be a vacuum. Here's proof of that. Photons that leave the sun travel 93 million miles, and then when they reach the Earth's atmosphere where there are some nuclei, that's when pair production will take place. But in a vacuum, it never takes place. So there has to be matter present. And yes, it's more likely in a solid than a liquid, and it's more likely in a liquid than a gas, but it will occur in all of those. So we have the energy greater than this number. Pair production can take place. And here's the magical thing about it. That gamma ray is converted from pure energy to pure matter. The gamma ray disappears, and in its place are formed a positron and an electron. That's total conversion of energy to matter, because what's the energy equivalence of an electron? I asked you that last week. We determined that if an electron is converted to pure energy, 511 keV. So if this positron and this negatron are formed, and each is worth 511 keV, that's 1.022 MeV. We have perfect conversion of this energy to this matter. So, and please note, the angle between the positron and the electron could be anything. I'm going to ask you a couple of times, what is it 180? And the answer will never be correct. It's not going to be 180. It's in some indeterminate angle, could be anything. Now, here's your diagram. This incoming photon, high energy, comes near this nucleus. They say it impinges on the nuclear field. That means it does not strike the nucleus. It's not hitting it down here. It's just coming close. Without that nucleus present, this cannot occur. So it comes close. The gamma ray disappears. And here's an electron and another electron, one plus, one minus. And we want to discuss briefly what's the fate of those two electrons. So first of all, you'll note that the angle between them is definitely not 180, not even close. So the fate of this electron here is that, let's see if I've got it on a slide. Yes. So the negative electron is going to undergo ionization events, knock anything in its path away, create an event, and eventually it will cool down and join all the other gazillion electrons in this world. Sorry, that's what happens to the negatron. But what happens to the positron always? The positron is going to do the same thing as the electron. It's going to undergo ionization events, and once it has cooled off and reaches its lowest kinetic energy, then and only then will the positron annihilate an electron and produce these two 511 keV gammas 180 degrees apart. The only thing 180 apart is an annihilation radiation. Nothing else qualifies for that. Okay, so the ordinary electron, the electron ejected cools down, becomes an ordinary electron. The positron ejected cools down, becomes a low energy positron that then can annihilate the electron and produce annihilation radiation. Now, I'm going to ask you a question in 2 minutes about this slide. Look what it says. It takes 1.022 MeV to form the pair. So the first 1.022 in energy is used up to form the pair. But what if it's not 1.02? Maybe it's a lot more. Maybe it's 3 or 4. The excess energy above 1.022 is shared equally by the two electrons as kinetic energy. Okay, so that means that let's say if we're 5.02 instead of 1.02, then these electrons would be ejected with a lot of kinetic energy. If this were exactly 1.022, the two electrons would be formed. They would have no excess energy. The positron would annihilate right away. So let's take a look at a couple of questions here. True or false? In pair production, the electron pair is emitted at a 180 degree angle to each other.
False.
False. True or false? A high energy positron immediately annihilates an electron in matter.
False.
That is false. Remember, we said a high energy positron can only create ionization events. It has to cool off, reach its rest mass, its lowest kinetic energy. Only then can annihilate. This is false because only a low kinetic energy positron can immediately annihilate an electron. So there are your answers to those. Now, how about this? I just promised you this question. We know it takes 1.02 MeV to form the pair, but we have a photon that's 3.02 MeV. True or false? The kinetic energy of each electron in the pair is therefore half of that value, or 1.51 MeV. True or false?
False. False.
True.
True and false. You know what that means, don't you? One of you is right. Okay, so let's take a look at the mathematics. The answer is in fact false, because what did we say? It takes 1.02 to form the pair. So we have to take the 3.02, subtract from it the 1.02 required to form the pair. That left 2 MeV left over. We divide that by 2, and the energy of the electrons will be then 1 million electron volts, not 1.51. You cannot forget, just subtract the 1.02 from the gamma ray energy to determine how much kinetic energy is going to be shared. Now, I want to go back to this question just to mention this came right off of an old exam. It didn't ask true or false. It asked you to calculate the energy, but it was not 1.51. It would be 1.00. Okay, now let's take a mental breather. We're going to take a relatively challenging in-class test on what we learned at the last hour of last time and the first 45 minutes of this time. So before we take this test, any questions about modes of decay or interactions of matter? Anyone? Okay, then I would appreciate it when you're ready to shout out your answer. Please just unmute yourself. I'd like someone in the class to answer every single one of the questions. Most of them are pretty easy, but there are a few challenging ones. I would consider this very easy. If I were you, I'd hope to get this question on my exam. The metastable state of technetium decays to the ground state of technetium, and that's an example of what mode of decay?
Isomeric transition.
C,
Isomeric.
excellent, isomeric transition. Now, please note, you're not going to see that G. I've already mentioned to you in the previous lecture that that's a teaching tool I use, but you're not going to see the G. So if someone asks you what's a half-life of technetium 99M, it's going to be 220,000 years, not 6 hours. Okay, good. So that's going to be C. And here's a descriptive answer, an explanation for you. I'm not going to read that through to you at all, but for every question, the answer will be right behind it. Okay. An atom is decayed, we really should say a nucleus is decayed by giving off a negative beta particle. The remaining atom is. Now, if you think back to the modes of decay from last week, and we said that in beta minus decay, the Z number always goes up by 1. Well, that's why we draw the arrow to the right. So let's go down each one of these and let's see. First of all, let's try to determine which one is correct. Let's look at A. It's going to give you an atom of a new element with a Z number increased by 1 and little or no change in mass number. Is that correct?
Yes.
Yes.
Yes. So that is the correct answer for the question. Now let's look at what's wrong with the other answers. In B, an atom of a new element, the Z number 1 higher than, that's correct, but a significant lowering of mass number, that'll never be correct. P32 decays to sulfur 32. Their mass numbers are the same within a few thousandths of a number. Okay, C, unchanged, you know that's wrong. It's decaying by beta minus decay. Let's see. Okay, yes, I guess there are some exceptions to that rule, like P32 decays to stable 30, sulfur 32, but it's not unchanged in the sense that it's not the same element. If it's beta minus decay, it'll always be a new element. D, an atom of new element with a Z number 1 less than, that's totally wrong. That only happens from the neutron deficient area, not the neutron excessive area. Little or no change in mass number, that is correct. So let's go back. Choice A is the only one totally correct. In beta minus decay, the Z number goes up by 1, mass number remains essentially the same. Here's the explanation for it. The internal conversion is most similar diagrammatically to which one of those? Remember I told you.
Is it photoelectric effect?
Correct. Photoelectric. Remember, photoelectric effect, the gamma is coming from outside the world and hitting the nucleus. And internal conversion, it's coming from the nucleus, knocking out an electron, and everything else in that diagram is identical. So yes, D, photoelectric effect, is a very lengthy explanation. I really spent a lot of time on these answers just to help you with your board review. This formula, the energy of an electron that's ejected equals the energy of the gamma ray that struck it minus binding energy. Which interaction does that describe?
Is this on photoelectric?
Good. That is photoelectric effect, because in that case, we could say that the energy of the ejected electron almost exactly equals the gamma ray that hit it, but we have to overcome that binding energy, which is a pretty small number. And so that is photoelectric effect. Compton effect, remember it had that really big equation with lots of Greek letters in it. So there's your explanation. Pair production takes place, A, only in the presence of nuclei, only in a vacuum, only in solids, or none of the above.
A.
Only in solids.
A, only in the presence of nuclei. Remember we said it can take place in a solid, a liquid, or a gas. So you must have nuclei there. I gave you the example that when a photon leaves the sun and travels through the vacuum of outer space, it will never undergo pair production. Okay, good. And there's your explanation. The literature value for the beta energy of calcium-45 is 0.255 MeV. What does that represent? Is that the average energy, the median energy, the maximum energy, or the root mean square energy?
C.
Maximum.
Excellent. We always use the literature value as the maximum energy, even though, hopefully you can see my image here, there's a spectrum of beta particles with all kinds of energies from slightly more than 0 up to Emax. Still, we use Emax as the literature value, even though not even 1% of all particles have that maximum value. Good. And there's your answer to that. In beta minus decay, the total energy is shared between the beta particle and
B.
B.
B, an antineutrino. Now, just for a little edification, remember that anti and negative mean the same thing. So one way to remember it is that a beta particle, which is negative, goes with an antineutrino, and a positron, which is positive, simply goes with a neutrino. Now, that's a matter of semantics. That's just wording. A neutrino is a neutrino, but we just distinguish a neutrino from antineutrino, just so you'll know that the antineutrino was associated with the beta particle. Okay, now, these are some true-false questions. They are some of the toughest true-false questions that I could think of related to positron emitters. So here's the first one. Positrons, you've all done PET scanning. Positrons are imaged following their interaction in a sodium iodide crystal. True or false?
False.
Okay. Good, false. Why is it false?
The annihilation event is what's being imaged.
Great, great. Do positrons even make it to the camera? They don't. They're electrons. How far do electrons go in human tissue? I won't say nowhere, but almost nowhere. Maybe they go a few millimeters. So the positrons cannot escape the body. And yes, you're exactly correct. We are imaging annihilation photons, not positrons. Okay. Beta plus emitting nuclides have previously undergone pair production.
False.
That is false. There is no reason whatsoever to think that is true. Positron emitting nuclides are formed by cyclotrons. They're not the result of some other kind of decay. So that's false. When a beta plus at its rest mass interacts with matter, how does it give up its energy? Is it by photoelectric and Compton effect?
False.
That is false. How does a beta particle lose all of its energy?
Is it annihilation?
Sure. It destroys a negatron and it releases annihilation radiation. What loses its energy by photoelectric and Compton? That's gammas. It's not positrons, that's gammas. So that's false. The process that competes with beta plus decay is called IT. True or false?
False.
False. What is it called?
Is it electron capture?
Excellent. Remember our diagram last time? I don't have it here, but the process competes with beta plus is electron capture. They both started in the same place and they ended up in the same place, but they are therefore they have to be competing, but they're totally different processes. One of them, the positron, has a broken line, a line down, and followed by the beta plus. So all 4 of those questions were false. Here's another good question for you. In alpha decay, which one of the following takes place? I'm going to let you read through A, B, C, and D, and then you can tell me what is the correct answer. Anybody?
C.
D like David?
No, C.
Like Charlie.
C like cat.
The Z number of the daughter is 2 less than that of the parent. I like that answer. And here's why. In alpha decay, it went from Z to Z minus 2. It went from A to A minus 4. So the answer to any part of that question is this. The Z number goes down by 2. The N number goes down by 2. The atomic mass goes down by 4. Those are the only possibilities. So choice C is the only one that could be correct. Greater than is totally wrong in both of those. And the A number doesn't decrease by 2. It decreases by 4. Good. Which one of the following, this is a common exam question, which one of the following processes occurs spontaneously when the neutron-proton ratio is too high? You're in the neutron excessive region. What's the only mode of decay that will do that?
A.
A. Great. Beta minus, right? That's the only mode of decay. You're going, let me back up to the question. The NP ratio. So let's take a look. What happened to the NP ratio? It went from N over Z to N minus 1 over Z plus 1. That is a decrease in the ratio. Remember, the ratio was too high. Now it went from N over Z to N minus 1 over Z plus 1. Okay, good. Some more true false questions. In the Compton effect, the energy of gamma 2 depends upon the energy of gamma 1.
True.
Totally true. In fact, what is gamma 2? It's the leftover energy after gamma 1 has had an inelastic collision with an electron. So true. In Compton effect, E of gamma 2 is entirely dependent upon energy of gamma 1. How about B? In the photoelectric effect, E of gamma 2 depends upon E of gamma 1. True or false?
False.
False.
Why is it false?
It relies on the binding energy of the electron, right?
Nope. It depends marginally on that, but no. Here's the real answer. Here is the real answer. There is no gamma 2 in photoelectric effect. What happened? The gamma gave up 100% of its energy. It's gone. There was no deflection. There was no partially elastic collision. So E gamma 2 doesn't even exist. So that can't possibly be true. In pair production, the electron and the positron and the electron are emitted at a 180-degree angle to each other.
False.
False.
That's an indeterminate angle, could be anything. D, a result of the Compton effect is pair production.
False.
That's false. The result of a very high energy photon interacting with a nucleus could cause pair production, not the Compton effect. E, now you have to think about this one. I'm going to tell you right now, well, let's see what you come up with for the answer. If you have a 511 keV positron formed in pair production, will that annihilate an electron in matter? True or false? Is that considered a pretty high energy positron? The answer is yes.
Right after the pair production, it wouldn't be able to annihilate.
Correct. And the reason is that the energy is way too high. If it were maybe 511 electron volts, maybe, but not 511,000 electron volts. So number one, if a 511 keV positron struck an electron, it would not annihilate it. It's got way too much energy. And number two, who said that the positrons in pair production are 511 keV? They're never 511 keV. It's false for both reasons. This is stating the 511 keV positrons in pair production. They're not 511 keV. They're, I don't even know, they could be anything, but they're not 511 keV. But even if they were, they cannot annihilate electrons, way too high in energy. So here's a very lengthy explanation for all the parts of that question. More true or false. Technetium metastable decays by internal conversion to the ground state.
False. Isomeric.
Good, false, IT. Beta plus decay competes with beta minus decay in many nuclides.
False.
False. This is from the this is from the neutron deficient region. This is from the neutron excessive region. It's one or the other. It can't be both. So this almost never ever happens where they compete with each other. C, an internal convergent electron. Now, many isotopes that we administer to patients produce internal conversion electrons. So this is applicable to all isotopes. Internal conversion electrons emitted from inside an internal organ lose about 10% of their energy in that organ. True or false?
False.
False. Approximately what percent do they lose in that organ?
No, it's almost all of it.
It's almost what?
100%.
Perfect. How far do those electrons go? They're not only low energy, but they're electrons. They don't go far. They only go a few millimeters. So they're going to dump all of their energy, not 10% of it, all of it into the internal organ. That's why we don't like internal conversion electrons. We don't like Auger electrons. They contribute nothing whatsoever to imaging. All they do is dose the patient. So we don't like them. How about this one? Technetium ground state, 220,000 year half-life, has been discovered in Siberia. Anyone? So if you look at a periodic table, there are brackets around number 43, and the footnote says this is a synthetic isotope. It never occurs naturally. And in fact, technetium number 43 is the only element under number 82 that has never been found in nature and never will be found in nature. Think about this. The Earth is 4.5 billion years old. Unless you had a half-life of billions of years or a stable nuclide, you'd never see it in nature. So technetium has none of that. It has no stable nuclides, and the longest half-life we know is 220,000 years. Now, compared to a human lifetime, that's pretty long. But compared to 4.5 billion years, that's like a microsecond. Okay. Characteristic radiation may be produced by the interaction of which of those would matter? Let's go down the list. Electrons. If electrons interact with matter and knock out other electrons, could they produce characteristic radiation?
Yes.
Yes. And how about anything else that can knock out an electron? Protons, photons, neutrons. Yes, 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 and yes. Those are all true. Anything that can knock out an electron, even visible light, will produce characteristic X-rays. They're all true. Okay, for these questions are regarding pair production only. True or false? Electrons and positrons are produced.
True.
True.
True. True. The incident photons must have energies greater than or equal to 1.02 MeV.
True.
True.
True. The total energy of the incident photon is divided between the kinetic energy of the positron and the kinetic energy of the electron.
False.
Good. Why?
Okay.
What's wrong with it? Remember we worked that little math problem about 20 minutes ago, where we had a photon was 3.02 MeV. So what's wrong with that statement? It's not the total energy of the photon that's divided by 2. It's the total energy of the incident photon minus 1.02. Remember, it takes 1.02 to form the pair. And so we have to subtract that from the total energy and then divide. That's why before we took 3.02, subtracted 1.02, when we got 2, We divided 2 by 2 and we got 1. The energy of the photon, of the positron, and the energy of the electron was therefore 1. Okay, the annihilation of a positron produces 1.02 MeV photons. True or false?
False.
False.
The 2 photons might total that, but they are not 1.02. They are 0.511 MeV. Okay, good. E, the E plus, the E minus and the E plus are emitted in opposite directions.
False.
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 That's probably the third time we've had that, but it's not a 180-degree angle. Okay, indeterminate. Now let's see, who knows? How does oxygen 15 decay? Alpha, beta minus, or beta plus? What kind of emitter is oxygen 18, oxygen 15? Anyone? So here's an easy way to remember this. There are 3 isotopes that are cyclotron produced that are only used by institutions who have their own cyclotron, and those are carbon 11, nitrogen 13, oxygen 15. They have very short half-lives, 20, 10, and 2 minutes. So it's impossible to ship them commercially. And so oxygen 15 is a positron emitter. Now, armed with that information, that it's a positron emitter, A, what happens to the Z number? When this decays, does the Z number go up or does it go down? So is A true or false?
True.
A is true. The Z number always goes down by 1. Just like in beta plus decay, it always goes up by 1. A neutrino is emitted.
True.
True. It's positron decay. The mass of the daughter is less than the mass of the parent.
True.
True.
That's always true. 511 keV photons are emitted. That's true.
True.
So guess what? They're all true. And here's what happens in positron decay. Positron is converted into a neutron plus a positron plus a neutrino. These 2 here are emitted, positron and the neutrino. These 2 share this energy, not equally, but an infinite number of ways. And so this is a balanced equation. 1 equals 1 plus 0. 1 equals 0 plus 1. And so all 4 of those questions had true answers to them. Okay, now if you think back when we just started last week, in the very first one of the slides, I showed you that if we plotted the Z number, the number of neutrons versus the number of protons for every known nuclide, we got a zigzag line that's gently sloped upward. So that was what's happening to the Z number as a function of the number of neutrons. So now, keeping that graph in mind, as the Z number increases, what happens to the number of neutrons in the nucleus? First of all, does it decrease or increase?
Increase.
It increases. As you go farther out in Z number, it takes more and more neutrons to make that nucleus happy. So it has to be B, C, or D. Those are the only ones that have increase. Okay, so does it increase the same as the Z number? That is it a linear increase? No.
No.
Does it increase, but the mass number remains constant? No. Does it increase at a somewhat greater rate than the Z number? Yes, that's the right answer. I think I might have a little graph here for you. Sure. So this is gently sloping upward. If it were linear, this line would have been a straight arrow like this, but that's not what it does. It takes more and more neutrons as the proton number goes up, takes more and more neutrons to keep everything happy. And so this is that from last week, this is that yellow band of stability that we saw. Radionuclides decaying by IT. Think technetium. A, emit only gamma rays. B, emit only X-rays. C, emit both of those. D, emit only positrons. Or E, can emit X-rays, gamma rays, conversion electrons, and Auger electrons.
E.
E.
Which one?
E.
B?
E is an elf.
Okay, good. Yeah, so E is the correct answer. We get all of these, X-rays and gamma rays, conversion electrons, and Auger electrons. So that is the correct answer. Okay. A nuclear transition involving only a change in state, an energy state, is called what and involves what? A, B, C, or D?
A.
Good. A is the correct answer. Just like with the case of technetium, the metastable state goes to the ground state. That's a change in state. What's given off? Only gammas. So A is correct. If it's isomeric, it can't be giving off betas. Nothing gives off neutrons. And so A is the correct answer. Which one of the following is not a likely product of the decay of a neutron-rich species? Neutron-rich means neutron excessive. It's got more neutrons per proton than it needs to achieve stability. So which one of those are you not going to get from a neutron-rich species?
E.
Beta plus.
Beta plus particles, not possible, because in neutron-rich, you're going to get beta minus particles. So beta plus is not possible. Good. Let's rank the following nuclides in order of increasing gamma ray energy. This is a question off of an old exam. So let's see if we can name some of these energies. How about xenon?
80.
80 keV, I-125.
28.
All right, let's even assume you don't know the numbers. Let's just say I would accept as an answer very low energy. The answers are 28 and 35 keV, but they're very low. So that will be the lowest of all. I-131,
364.
good. It's the number of days in a year, 364.4. Technetium is, of course, 140. How about cesium? So cesium is 662. We don't ever use it in patients, but we do use it for calibrating a dose calibrator and other calibration exercises. So the lowest will be iodine, followed by xenon, followed by technetium, then this iodine and cesium. So that would be 2, 1, 4, 3, and 5. That's choice C. And there it is. There are your energies. Okay. Electrons are emitted as a direct result, underline direct result of which of the following processes? Anybody?
B.
Was that E like Edward?
B like Bob.
B like Bob? That is actually the correct answer. Internal conversion, remember the nucleus releases energy, knocks out an electron. In Compton, a gamma knocks out an electron. Photoelectric, a gamma knocks out an electron. Those are direct results. Isomeric transition doesn't emit the electron, that's emitting gamma rays. And electron capture, the only time that that would emit an electron is Auger electrons ultimately. Those two are, this is indirect, this is not even applicable. So 1 and 3 and 5, choice B. That is correct. Okay, this is right off an old exam. The energy equivalence of the rest mass of one electron is
A.
A, 511 keV. And that's by Einstein's equation. Gamma rays from technetium are most likely to undergo photoelectric effect in which one of those?
B.
B, the lead colorimeter. Remember we said that it's proportional to density cubed, or more accurately, the Z number cubed. And that lead colorimeter is much denser than anything else you see on that screen. So certainly the lead colorimeter, and keep in mind, it's that cubed relationship. Okay. Radiation emitted by a radioactive source decaying by electron capture may include. Now, take a look at the answers. What it's telling you there is that in every case, 4 of them are emitted. So if you know any of the one, if you know one that cannot possibly be right, that will tell you what your answer is.
E,
Um,
as in Edward.
let's see, which one was it?
E, as in
E.
Edward.
E like Edward, sure. You're not going to get a beta particle emitted from electron capture. I guess it's possible it could be a positron because those are competing modes. You would never get a beta particle. So anything with number 1, which is A, B, C, and D, can't possibly be right. Process of elimination, it has to be choice E. Okay, and this is the very last question on the test. I don't think I even mentioned full width half maximum energy resolution before, and I'm not an instrumentation expert, but this question is on exams so often that I've put it in the notes here. So the full width half max energy value, that means the full width of the peak in energy units divided at half the maximum height. And so all we do is we take the width of the peak in energy units, that's this width right here at half height. Here's the height, go halfway up. This is 70 keV. We divide it by the known photo peak energy of the nuclide, which in this case is cesium. You don't have to really know that. And so we're going to divide 70 by 662. And what are we going to come up with? What percent?
9.5.
Sure.
D.
10.6.
10.6%. Sure. Here's your math. 70 divided by 662 is 0.1057 times 100. So roughly 10.6%. Now, let me back up and ask you another question. If this is your well counter and you did a full width half maximum test on it, and you came up with 10.6%, are you happy with your well counter or not? Now, there's no specification that's nationally mandated, like for dose calibrators, everything has to be within 10%. There's no magical number here, but you should know that the best detection device is going to be between 6 and 10%. That is considered the optimal range. And so if your well counter comes up with 10.6%, that is out of the range of acceptability. And so you need to either get a new well counter or at least replace the sodium iodide crystal that's in there. So that was the last question on that part of the test. Now, here is the really good news. Believe it or not, we are finished with all of the physics, and everything else from now on out is going to be a lot more descriptive. We're not going to need calculators. There may be some tangents that we run off on with a physics question here or there, but pretty much we are done with the physics, and we're going to start with isotope production. We're going to talk about isotope production and generators today. And then the next part in the 5th lecture, we're going to start on radiopharmaceuticals. We're going to spend 2 or 2.5 lectures on that. We're going to cover a complete lecture on current NRC regulations and hot lab quality control. We're going to talk about radionuclide therapy and internal dosimetry and in vivo non-imaging procedures. And a lot of stuff to cover. And the last lecture or 2, we're going to spend a lot of time on mathematics. And I want to reserve some time during the last 2 lectures for one other thing, which I have not done with classes before. You all probably have a collection of old questions or books that have questions. There might be some questions you're struggling with. You can't come up with the right answer, or maybe you disagree with the answer. So for lectures number 11 and 12, please plan to bring in any questions that you have that I might be able to help you with in class related to the topics that I'm teaching to you. Okay, any questions about anything we have covered in the last 7 hours? Any question from anyone about anything? Okay, then we're going to start the radiopharmacy part, and I think you'll agree that radiopharmacy would not exist if it were not for radioisotopes. And so we want to take a good look at the methods of production. There are 4 methods of production of isotopes today. One of them, the thermal neutron reactor, is rarely used anymore. There are several generators that are commercially available. The fission reactor produces 3 of our most important nuclides. And of course, cyclotron produces 6 of our most important nuclides. So one of the questions you are going to get on your exam is the following. Here are 4 lists of nuclides. Which one of those lists is, reflects that those nuclides are generator produced or cyclotron produced? By the end of this lecture, hopefully you'll have a good handle on that. So we're going to start with generator produced, and then last few minutes of the lecture, we're going to cover the last 3: fission, thermoneutron, cyclotron. So to understand generators, we need to understand what equilibrium means, and we're going to tackle that first. That does have some little bit of mathematics to it. But equilibrium is a condition that's established when we have a mixture of a parent and a daughter. And the only condition is that both are radioactive and that the parent's half-life has to be longer than the daughter. Or as this slide says, the daughter's half-life has to be shorter than the parent. So anytime you have a parent decaying to a daughter and the daughter's half-life is shorter, equilibrium will be established. Now, there are 2 kinds of equilibria, secular and transient. And what they really have to do, it's almost more a matter of human perspective than anything, but what they have to do with is what's the ratio of half-life of parent to daughter? We'll see that in transient equilibrium, it's going to be around 10 to 1. And in secular equilibrium, it's just going to be a really big ratio, 100 to 1, 1,000 to 1, 10,000 to 1, 100,000 to 1. Well, here's a good example. Number 1, secular equilibrium. This is a condition that exists when the half-life of the parent is very, very much longer than the half-life of the daughter. It might be 100, 1,000, 10,000. Here's a great example. Radium in the soil decays to radon. This is the radon that we're concerned about in the atmosphere because we know that over half of all lung cancer patients have their disease because of radon. We can't get away from it. We're probably breathing very, very tiny amounts right now and also for our entire lives, but it's there. So look, we have radon 226 going to 222. That makes sense. This is alpha decay. It dropped, the A number dropped by 4. Radium going to radon, the Z number dropped by 2. And look at the huge difference in the half-lives. This is 1,620 years. This is 3.8 days. That ratio is almost 156,000 to 1. And so what we're expecting to see during 10 half-lives of the daughter is essentially 0 decay of the parent. Yes, we know it's decaying, but the decay rate for this is so slow that across 38 days or maybe 5 weeks, whatever that is, 4 or 5 weeks, we're going to see essentially no decay. Yes, there is some, but it might be, 0.001% a day or some tiny amount. So let's take a look at the graph. Keep in mind, what we're looking at is how much decay of the parent takes place during 10 half-lives of the daughter. Now, as you'll see in this diagram, from time 0, let's say we have a parent and daughter in equilibrium. We took the daughter off of the generator. So now here's what happens. The daughter builds up very rapidly. Then the activity begins to taper off. And right here, where there's an intersection of the parent line, remember, the parent is always in the generator as she's decaying. And here it's a flat line because we only went out 38 days, but the half-life, as you can see, was 1,620 years. How much decay do we expect to see? 0. Is it decaying? Of course it is. But this is a flat line because we only went out 38 days. If we had gone out 38 years, the line would have come down like this. Now, so the daughter built up rapidly. Right here where the lines become parallel, that is where equilibrium is reached. And the lines are not only parallel, but superimposable. Now, they're only superimposable typically in secular, not in transient at all. They might be, but almost never. So I asked you this question in the very, let's see, I believe in the second lecture. We were studying radioactive decay, and I asked you, true or false? Parallel lines on a decay curve, does that mean that the isotopes have the same half-life? And the answer, of course, was yes. So here, let me ask you this. If this is the radium and radon decay, do the parent and daughter have the same half-life, or do they appear to have the same half-life?
They appear to have the same half-life.
Correct. We know they don't have the same half-life, but here it looks like they do. The lines are parallel and superimposable. They look like they do. So look what we say for all equilibria. For secular, we say that the daughter appears to have a half-life. We call it the apparent half-life. The daughter has a half-life that appears to be the same as a physical half-life of the parent. Now, believe it or not, this makes sense. The daughter can't decay until it's formed. It's being formed with a very, very long half-life. So the decay of the daughter is entirely dependent upon the decay of the parent. And that's why the daughter looks like it has the parent's half-life. It can't decay until it's formed. It's being formed by the parent's half-life. So the daughter appears to have the physical half-life of the parent in the equilibrium, but truly they have their own half-lives. When we remove this daughter, it has its own half-life. So this is an apparent half-life. They appear to be equal. Now, we're going to take a practice exam. I'm sure you're getting used to that concept now at the end of this lecture. And I'm going to ask you a question about this equation. Now, transient equilibrium is different because the ratio of half-life parent to daughter is around 10 to 1. Now, here's what that really means. 8 to 1, 10 to 1, 12 to 1. It does not mean 25 or 50 or 100 or 1,000. It means around 10 to 1. And what is the classical example? Look at the Molytech generator. We have a 67-hour half-life parent and a 6-hour half-life daughter. The ratio of 67 to 6 is 11 to 1. That's pretty close to 10 to 1. This is the classical, the perfect example of transient equilibrium. So this is reached when the half-life of the parent is about 10 times as long as the half-life of the daughter. And we'll take a look at the diagram in a moment. Now, here it is. You see here that from the time we last removed the daughter builds up very rapidly, tapers off, and right here where the lines intersect, and probably even a better way to look at it is where the lines become parallel is right here. Once the lines become parallel, then it's in equilibrium. And what do we say about parallel lines? Same half-life, correct? And I'll ask you this same question. Are the half-lives of parent and daughter equal? Or do they appear to be equal? And of course, the answer is same as before. So this equation is true of all equilibria, secular and transient. Now, let's go back here. Very infrequently do we get the case where the daughter's activity slightly exceeds that of the parent. This straight line is the parent. The molybdenum in the Molytech generator is a straight line. It's always in the generator. We never take it off, and it's that straight line. The daughter builds up, reaches equilibrium. The lines are parallel, and so the daughter appears to have the half-life of the parent. Remember, technetium can't decay until it's formed. It's being formed with a 67-hour half-life. So the technetium in the equilibrium mixture is going to look like it has a 67-hour half-life. We know it doesn't, but in that mixture, it does. Now, technetium's curve looks like this, except for one thing. This line here is actually below the molybdenum line down here. It's very unusual for this activity to exceed the parent. It can do so by about maybe 5%, but we don't see it very often. And in technetium, we don't see it. It just comes down parallel, right down here. Okay. Now, if you had your lecture notes in front of you, I would tell you put a big star by this first item. It's a common exam question. I'm going to ask you this question on the exam, but in a slightly different format. How long does it take to reach equilibrium? What's the rule of thumb? Lucky for you, the math is easy. If it's transient equilibrium, we simply say we're going to take 4 times the daughter half-life, and that's going to be our estimate. Look how accurate it is here. 4 times 6 hours is 24. It actually takes 23 hours. So that's a very good rule of thumb. For transient, it takes 4 daughter half-lives. For secular, it takes more like 6 daughter half-lives to reach equilibrium. Now, this 23 hours is a good number to know. For technetium, that is only applicable to technetium. But keep in mind, if you don't know how long it takes to reach equilibrium, you could always multiply 4 times the daughter's half-life. Now, any questions about equilibrium before we proceed to generators?
I actually have a question.
Sure.
So if we look back at the transient equilibrium, like the graphs, actually for both of the equilibriums, like the log of activity, how, like conceptually, how is the daughter increasing to begin with? Sorry, I know it might be a stupid question, but.
No, first of all, there are no stupid questions, not ever. You mean, how is it increasing?
Right.
Yeah, so keep in mind, let's say we just diluted the generator. How much daughter is there at that moment? We just diluted it. How much daughter is now present? Basically 0, right? Basically 0. But the molybdenum is decaying continuously. It's always decaying. It's a random process. It's going on eternally till it's all gone. So the daughter is being formed and it's accumulating much faster than it's decaying. And then as time goes on, the production rate of the daughter slows down. And once it reaches equilibrium, this is the point where the daughter and the parent are at equilibrium. It's being formed and it's decaying at exactly the same rate. And that's where the lines become parallel. I hope that helped. Did that help?
I think so, kind of.
It's not that simple a concept. Truly, it's not. But you can just see that as a function of time, the daughter builds up very rapidly. Now, here's an old exam question. What if you wait 1 hour and elute the generator? Are you going to collect 0? The answer is no. That equilibrium means that it's always decaying. You're always going to collect something, but it won't be much. If you go out 5 or 6 hours, it's going to be better. And you go out 20 hours, even better. The daughter just keeps increasing because it's being formed faster than it can decay in the equilibrium mixture.
Okay.
Okay, I hope that's helpful somewhat.
Yeah, thank you.
Okay. Now, what is a generator? A generator is a self-contained device. It contains a parent and a daughter that's a mixture and equilibrium. It could be secular, it could be transient. Later on, I'm going to show you a list of generators and ask you, is that in secular or transient equilibrium? And the purpose of that generator is to produce a daughter for a totally different purpose than the parent. The parent's only purpose in this life is to produce a daughter. The purpose of the daughter for us is to perform diagnostic studies. So the reason we're using this is simply to produce a valuable radioisotope for performing diagnostic studies. So keep in mind, self-contained system, you carry it around. We have that mixture in equilibrium, and it's simply producing a daughter. We remove the daughter, and it produces more daughter. You know, many years ago, generators were called cows. You might have heard that before.
No.
The Mallinckrodt generator is called the Ultra Technic Cow, KOW generator. And when I first started many, many decades ago, we talked about milking the cow. Nobody said, I'm going to elute the generator. We said, we're going to milk the cow. Think about how it works with a cow. Farmer milks the cow, comes back tomorrow, there's more milk. The farmer milks the cow again, comes back the next day and the next day, and every day there's milk. Now, if you look over to my image just for one moment, here's what you've got. The milk production in a real cow, a four-legged cow, is a flat line. That milk is not radioactive, the cow is not radioactive, so nothing is decaying. So you have milk production pretty much the same day after day. But in our cow, because the milk is radioactive, we're seeing it go down every day. So we have to adjust the volume we elute every day because the activity of the technetium being produced is going down every day because the activity of the molybdenum parent is going down every day. So we'll talk a little bit more about that in a moment. Why do we even need generators? Let's say you own a company that owns all the molybdenum in the world, and you're located in Chicago.
Hi, Cheryl, give me a call. Stay on me.
Let's say that you own that company and you have a customer in California who wants you to ship technetium to the customer. If he orders 1 curie, let's say that you could ship it priority 1, FedEx priority 1. You could get it there in 18 hours. 18 hours is 3 half-lives. What fraction remains? 1/2 to the 3rd power is 1/8. That means that for every 8 millicuries you put in that box, the person on the recipient end is only going to get 1. So to ship somebody 1 curie, you have to put 8 curies in the box. There is not enough technetium on the planet in any one moment to supply one country, much less the entire world. And that's why we have to use short-lived generators to produce short-lived isotopes, because the shipping time is so long compared to the half-life of the isotope that it's just not possible to ship things all over the world. So generators are simply used to produce short-lived isotope where it's not feasible to do the shipping. And read this sentence carefully. The parent's half-life has to be long compared to the travel time to make sure that the person receiving it gets the adequate amount. Now, let's think about this. Let's say the shipping time is 18 hours. But the half-life of molybdenum is 67 hours. So we're going to take a wild guess and say, how much are we going to lose in that shipping time? Let's say it's 30%. Okay, we can afford to lose 30%. We'll just put an extra 35% in there. We can't afford to lose 87.5%, which is what happens shipping it from Chicago to California. So we want a long travel time for the generator long half-life compared to the travel time, long half-life of the parent. Now, these are the 2 commercially available generators sold in the United States. The one I'm familiar with is this one, the Technolite generator. And you're going to see a photo of the front of it in a minute in a minute where it's been cut off so you can see the internal parts. Now, if you read carefully, this says here, Bristol Myers Squibb. That company has not sold generators in 20 years. That shows you I'm a pack rat and I save things for a long time. But this was a valuable save because it enabled me to take photos of it and show you what it really looks like. The Mallinckrodt generator, the Ultra Technical generator, they're both cylindrical. They both work the same way, just sold by two different companies. Now, when we as radioisotope chemists develop generators, we do so with about 7 or 8 properties that are ideal to all generators. These are generic to any generator. It doesn't matter what the half-lives are, what the parent is, what the daughter is, what the purpose is. Every generator system has to meet all the following properties to be considered ideal or perfect. Number one, the output from the generator has to be sterile and pyrogen-free. Sterile means, in the short sentence, it contains no life forms. We think about bacteria, but if it's sterile, it has no bacteria, no viruses, no spores, no fungus, nothing that is either alive or could generate life like a spore. It's sterile. If it's sterile now and it's in a sealed container, 100 years from now, it'll still be sterile. What does pyrogen mean? A pyrogen is a substance that causes a fever, febrile reaction in a patient. By federal law, everything that's injectable must be sterile, pyrogen-free. So I think you'll agree that any drug that we administer, as well as the output of the generator, must be sterile and pyrogen-free. Number two, the chemical properties of the parent and daughter have to be different. Otherwise, how could we separate them? And fortunately, every parent in every generator decays to a different daughter, a different element. We can always separate one element from another. We can't separate technetium metastable from technetium ground, but we can certainly separate technetium from molybdenum. Pretty easy to do. So these have to be different. Chemical properties have to be different so we can separate them. Number three, ideally, we want to elute the generator with physiological saline, 0.9% sodium chloride. We don't want any violent reactions. We don't want to have to aseptically adjust the pH with sodium hydroxide or hydrochloric acid. That's a very easy way to break sterility. We just want to put saline through that column, collect the eluate at the bottom, and use it. Number four, we want the daughter isotope to be short-lived. That means typically hours or days, although we do have a generator producing an isotope, rubidium-82, which is 75 seconds. That's okay, not ideal, but workable. So we want a short-lived isotope, and we would like it to be a pure gamma emitter. Why don't we want beta minus emitters or beta gamma emitters? For diagnostic studies, they just increase the risk to the patient. We can't image the betas. All they do is confer a radiation dose. So we want it to be short-lived and a pure gamma emitter. Number five, we want the half-life of the parent to be long and short. Now, you know that that's not possible. It's just one number. So we want the half-life of the parent to be short enough that the daughter grows in very rapidly, but long enough for it to have a good shelf life. And we consider the molybdenum perfect. It's long enough that the generator actually lasts us for 2 weeks, and yet it's short enough that we can generate curies of technetium every single day for at least the first few days of the life of a generator. Number six, the daughter chemistry has to be amenable to the preparation of lots of different kinds of cold kits. And you know that we have 3 bone agents and 2 hepatobiliary agents, and a lung agent, liver agent, and a number of other kinds of agents I can't even think of right now that are in kit form. We simply take technetium, add it to the vial, mix it up, swirl it a little bit, let it sit for 5 or 10 minutes, perform quality control, and we're ready to go. Those are called cold kits, and some people call them shake and shoot kits. We add them up, we add the technetium, we shake it up, wait 5 minutes, do QC, and then shoot it into the patient. reminds us of shake and bake a little bit, I suppose. Now, we also want, what about this? We want a very long-lived or stable granddaughter. We don't want to confer significant dose to the patient and also possibly to subsequent generations. Now, what's a very long-lived isotope? How about technetium ground state? 220,000 years. How much decay is going to take place in a person's lifetime? Almost zero. The fraction decaying per unit of time is only 3 millionths of it per year. It's almost nothing. We prefer it to be stable, but if it's not, that's okay, as long as it's very long lived. Number 8, and this is just a common sense thing, we need very inexpensive, think lead, very inexpensive and effective shielding for the generator. Lead is a very soft metal. It can be molded to any shape imaginable. And in fact, 48 pounds of lead are in that 48.2 pound generator. The other couple of ounces is simply the fluid path, and you're going to see a photo of that pretty shortly. And that will minimize the radiation dose to the people who are handling the generator, who are shipping it, who are handling it, who are carrying it down our hallways and so on. Okay. Now, this is a sketch of the chromatography column that's in that generator. Inside this column is a finely divided white powder. It looks almost like sugar. It's more like confectioner's sugar than real sugar. But what is it? Chemically, it's aluminum oxide. The formula is aluminum, it's dialuminum trioxide, Al2O3. But the trivial or the common name is alumina. We call this an alumina chromatography column. Now, the two terms here, they look alike and they sound alike, but they're very different. The eluent, ANT, is the solution that we put down the column. That would be sodium chloride solution. The Lu8, ATE, is what we collect on the bottom. That is pertechnetate. You'll note this is an anion, a negative ion, and has a -1 charge. And that is what we desire. We never want that molybdenum to come off. And so what's in this glass column is simply aluminum oxide. And you'll see shortly that the affinity of molybdenum for this aluminum oxide is infinitely high, and the affinity for pertechnetate is infinitely low, and it simply washes right off. Now, this is the backside of that generator whose photo I showed you a couple of minutes ago. And this is the guts of the generator, and I had the manufacturer cut the front off for me so you can see it. Now, I want to show you all the different parts before we discuss the process. This little filter right here on the top left is not just a sterile filter, but more importantly, it's a sterilizing filter. It's very porous, it's open to the air in the generator, and it guarantees that this side of the generator is always going to be at a pressure of 1 atmosphere. Remember, air is in that generator, it can get in and out, and if you ever had a vacuum on this side, air would simply flow in here to break the vacuum. This is a port, and remember, you're not going to ever see any of this sealed up, but this is the port where the manufacturer injects the molybdenum. He injects it, goes down this outer teeny little tube, gets to the column, and hits the generator, and right here, you can see a slightly darker area, and that's where the molybdenum is located, right here. It never moves. It sits there for the life of the generator. These teeny little hollow tubes are the fluid paths up here, and you can't see the top of this generator, but up here, there are 2 needles sticking up. One needle is connected to this inner tube here, and the other one is simply sticking up, and it's connected to the filter so air can flow through this, through the other needle into the vial, create a head pressure, push the liquid down the column, down like this, goes up the other side. It goes through this 0.2 micrometer filter that will remove any pathogen, and any particles that might be there. Maybe a fleck of aluminum oxide got in there. This removes anything particulate, and then we collect a clear, colorless, sterile, pyrogen-free solution. So those are all the parts. Just rename a couple of them. The sterilizing filter, the port where the manufacturer puts it on, the fluid path. This is your column, the aluminum oxide column. All this background, this grayish looking area is the lead shielding, fluid path again, and the filter. Now, this is a schematic that's going to help you to understand what drives the flow of liquid in here. And the driving force, in fact, is this. This is a sterile, evacuated vial. It collects up to 30 milliliters. It is a very hard vacuum. The amount of air in that vial is as close to zero as it could possibly be. So how many atmospheres of pressure are in this vial? 0. How many are on this side? Always 1. So when you put the evacuated vial on this side, and you'll note this is a shielded, lead shielded evacuated vial. When you put an evacuated vial on the needle on this side, air is going to flow in this filter needle, bubble up, push down the liquid. The liquid's going to come down the column, flow through all the tubing, go through the filter, and collect in this evacuated vial. And it will keep flowing until the pressure equilibrates, and then it'll stop. And that takes typically 3 or 4 minutes. We don't ever sit and watch a generator. That's about as much fun as watching paint dry. But we know that it takes about 3 or 4 or 5 minutes. So we start the dilution, we walk away and do something else, come back in 4 or 5 minutes, and it's ready to go. So the driving force here is this evacuated vial. Okay, any questions about that diagram before we move on? Anyone? Okay, good. Now, every generator has a label on it, and the generator has what we call a bar 3. You can see 3 red bars here. The only thing that we receive that's hot enough in a box for a bar 3 is a generator. All the other labels that we receive are typically bar 2, all of our radiopharmaceuticals. A bar 1 label would be for like a cold kit with 20 microcuries in it, not millicuries, but microcuries. So a bar 3 label, this is called a yellow 3 because the top is yellow. The other labels would be a yellow 2 and then a white 1. The white has no yellow on it at all, but they all have the radioactivity symbol. Okay. Now, everything I said is summarized in the next 2 slides, so I'm not going to read it to you, but I'm going to hit the highlights. Prior to the shipping, molybdate is immobilized on the column of aluminum oxide. It's immobilized because it has very high affinity. Molybdenum aluminum oxide, very high affinity. We pass saline down the column. We collect it in a sterile, shielded, evacuated vial. That is called the LU8. It is in the chemical form of pertechnetate. And we have quantitative retention on the column and quantity of molybdenum and quantitative removal of pertechnetate because of the huge difference in the affinity of molybdenum for aluminum oxide compared to technetium, where there's no affinity at all. Okay, that's why it works. So the driving force, again, is this evacuated vial. And one thing to note, if you've ever dealt with a generator, is that molybdenum is decaying every single day. And so as the week rolls on, Monday to Tuesday to Wednesday to Thursday to Friday, we have to adjust the volume every day so that we get the same radio concentration every day. That's important for a couple of reasons, one of which is it helps us to catch a problem. If you know that every single day you should get 150 millicuries per milliliter in your generator, and one day you've only got 90, you know there's a problem. If you were to elute with the same volume every day, you would never be aware there's a problem because the concentration would vary all over the place. Also, you want to control this concentration to be very high first thing in the morning so that you can get a bolus injection with a very small volume. That's also important. So this, I took 20 and just used the 24-hour decay factor for a 67-hour isotope, And that's what this is. This is a 24-hour decay of the isotope, but I've decayed the volume, which works perfectly. So you'll note that down here on Friday, we're only collecting 7 milliliters. That's a third of what we collect on Monday. That means we're also collecting about a third of the activity. And therefore, we often have to elute multiple times on Friday, at least 2 times, especially if the department is pretty busy. Now, these are 5 generators. 4 of them are still available. Generator number 2 is not. I'm going to briefly describe each of these, and then I would like you to tell me, is it in either secular or transient equilibrium? Here's the first one. This is a research generator, but gallium-68 compounds are available. We can make this in our lab. This is a positron emitter. And take a look. This is a germanium gallium generator. This is the parent. This is the daughter. Look at the ratio of half-life to parent to daughter. 275 days to only 1 hour. What's the type of equilibrium?
Secular.
Secular.
Secular, 100%. Huge ratio. I don't know what it is, but 100, definitely secular. This generator is no longer available. Many years ago, probably 20, 25, you could buy a rubidium krypton generator that produced krypton 81M. This is a noble gas, one of the noble gases like xenon and neon and argon, and it was used for ventilation studies. And here was a problem, a couple of problems with it, really. Number one, the half-life was 4.7 hours. That means that 24 hours, 1 day, was 5 half-lives. How much remained? 5 days. 5 half-lives per day. That means it went from 100% to 3%, 1 over 32. 97% is gone. So one of the problems was you had to buy this generator every single day, not knowing whether you were going to have a ventilation study or not. Cost prohibitive. And also look at this, 13-second half-life. Produced beautiful images, but it was impossible to look at washout because in 1 minute, you had gone through 5 half-lives and 97% of it was gone. Or maybe, 1 minute, 4 half-lives, over 90% was gone. What equilibrium would this be?
Secular.
Secular, we have 4.7 hours and 13 seconds. Strontium rubidium generator, readily available all over the world. Rubidium is a cardiac imaging agent, a myocardial perfusion imaging agent with a 75-second half-life. You can see it's positron. Strontium rubidium generator, parent and daughter, 25 days, 75 seconds. Type of equilibrium?
Secular.
Good. So we have so far all secular. The Molytech generator, which we just spent a half hour on. What is that one?
Transient.
Transient.
Good. Transient, 11-to-1 ratio. And the very last one, I've actually used this generator, but it was about 45 years ago. The tin indium generator is available today. We would never use it in the United States because the energy is almost 400 keV. The half-life, we could probably live with an almost 2-hour half-life, but the energy is awful. Where it's used is there are some small countries in Africa that are so poor that they simply cannot afford to buy a Molytech generator every week and ship it to Africa. It would cost thousands of dollars a week. They can't afford it. Some of these small countries only have one gamma camera that one of the companies gave to them, probably a 5 or a 10-year-old camera. And so the quality of their imaging is not so great. I mean, the energy is too high. You can bind indium to lots of compounds, just like technecium, but the image quality will never be good. So this was a 118-day half-life. That's really good for shelf life. It would have had a shelf life of 6 months, but the image quality was poor. What kind of equilibrium is this?
Secular.
This is secular also. So all of these are secular except, of course, this one, which is transient. This is a decay scheme for molybdenum. And this says molybdenum decays by beta minus decay to the ground state. This decays by IT, to the metastable state. This decays by IT from metastable to ground. This further decays by beta minus to ruthenium, which is stable, but the ground state has 220,000 year half-life. Now, if I had not told you the modes of decay and only showed you the arrows, would you have known the modes of decay? And I know you would have. This is an arrow from left down to right, beta minus decay, the only arrow drawn to the right. IT is straight down. Here's another beta minus decay. You would have known that automatically. So why does a generator weigh 50 pounds? Now, it will shield all of these, but specifically, why do we need 50 pounds of lead? 5 pounds of lead would shield technetium. We wouldn't need 50 pounds. So the answer is choice A. It's to shield the molybdenum parent. The photons from molybdenum are 740 and 780 keV. They are so high that the amount of shielding just for technetium would not be adequate, especially because we have curies in there. And so the real reason we need 50 pounds is to shield the molybdenum parent. Now, let's take a look at this question, and we'll wind this up within the next few minutes. We know that sulfur colloid never clears the liver. We humans cannot get rid of it. So if you get a sulfur colloid injection 100 years from now when you die, it's still in your liver. It means absolutely nothing. It's not harmful, causes no problems ever. But think about this. All the 99M technetium decayed to the ground state, and you now have a liver with a radioactivity of 220,000 years. Are you worried about that? If it's the patient or even yourself, are you worried about having a liver with a 220,000 year half-life? Yes or no?
No.
Definitely no. Why are you not worried? Here's the mathematical answer. If you say that lambda is 0.693 over T1/2, if you take 0.693 and divide it by this number, look what you get. Only 3 millionths is decaying per year. That is such a tiny number that it's not even significant compared to our background radiation. Which is more dangerous, a 10-year isotope or a 1-year isotope?
The 1 year.
1 year is definitely more dangerous. All of it's going to decay in your lifetime. Perhaps, unless you live to be 100, a 10-year half-life, it's not all going to decay in your lifetime. What does this pattern represent? It actually has a name. What's going on here? Look at the pattern here. What are we doing? Okay, so this is called an elution profile. And here's what we've got. We let this build up, and at 24 hours, in one instant, we take it all off. Again, we let it build up, and we take it all off. This is 5 sequential elutions of a generator, equally spaced in time. It could be a Molytech generator. We're going from here to here. This is 24 hours and 48, 72, 96, 120. But this could also be a 1 minute half-life where we eluded every couple of seconds. That's a bad example. Let's say it might be a 1 hour half-life where we eluded it every 5 minutes. And you still get a pattern like that. So as this says, it's equally spaced solutions. It's in transient equilibrium. And how did you know that? Because this line is not a flat line up here. And during the 10 half-lives of the daughter, we see a lot of parental decay taking place. So this is an elution profile for a generator in transient equilibrium. And the pattern here is simply equally spaced in time elutions from that generator. Okay, it is exactly 11 o'clock. We're going to stop here, and the test on radionuclide generator will be the very first thing that we do next Tuesday. Let me stop the share just for a moment, and I can see a lot of pretty faces out there, so that's nice. And any questions from anyone about anything. Hopefully that's a good comprehensive review for you, give you a new insight into equilibrium and generators, and give you a little bit stronger feel about it and about answering questions. Any questions from anyone about anything we have covered?
I was curious about the practice exams, if they are timed, and then if you can start them and come back.
The answer is they are not timed on purpose. I set it for no time limit. And yes, there is a link there that says, I don't remember the exact wording, stop now, continue later, something of that sort. So yes, you can pause it and come back. You'll have to use exactly the same login that you used before, but yes, you can come back and complete it later.
Thank you.
Yes, and also I noticed that some of you are taking practice exams, but a lot more of you, and I think this is a really good thing, a lot of you have been taking the tutorials, studying the tutorials and taking the tests. And that is a wonderful way to assess your level of knowledge in a pretty short test, 10 or 20 or 30 questions on different topics. And in particular, one of the ones I'm going to recommend that you do somewhere along the line is that there is a 50 question test on current NRC regulations and hot lab quality control. And I think that would be a very valuable one to take. Yes, any other questions about anything, the tests or tutorials, anything at all? So if you have not taken the tutorials and you choose to do so, one of the 3 links, it's going to say, here's a link to the tutorial that you can study. Here's a link to the test. And here is a link for making a payment. Don't make a payment. Please don't make a payment. They are free for students. When you are board certified and you want to get continuing education credit, you can come back and take these tests all over again and earn continuing education credit if you wish to. And then you'll have to pay. It's still a pretty nominal charge, but you will have to pay. But now they're free for students. There is a limit, however. You may only take any of the tests, whether it's the 100 question tests or the tutorial tests, 3 times. And then after that, you won't be able to take it. No one should need to take any of those tests 3 times. I'm hoping you won't have to do that. Any other questions? Okay, if not, thanks for your attention, and I will see you next Thursday morning at 9 a.m.
Thank
Good.
you.
Thank you.
Doctor.
You're welcome. Have a good week.